All right, good morning, everyone. Thank you for joining us with our presentation for our Capstone. Today we are presenting our Capstone project for Sterling Highway reconstruction of miles 157 to 169. This focus for our alternative analysis for our Anchor River Bridge crossing. This project is completed with the help of DOT and our client, Aaron Hunting. On behalf of ASA, our Arctic Solution of Alaska HR firm. My name is Renato Speo. I'm the project manager of this team, and presenting with me right now is Orion and Joe. The rest of our team is Ben and Tessa. Also, I want to acknowledge and thank those professional mentors that helped us complete this project. We have Chris Fose and Nicholas Mary from the DOT, and also Richard Pugo from Dow. Also, I want to thank our faculty advisor, Dr. Joe Yang. Today, we'll talk about our project background, our design criteria, also we'll walk you guys through our decision matrix, how we complete all those projects, and our alternative analysis between roadways and bridge, and also our cost estimate, and we'll end up with our lesson learned. We'll begin with our project location with Joe.
Okay. So located in Anchor Point, just north of Homer, Alaska, near the intersection of the Sterling Highway and the Old Sterling Highway, we'll be focusing mostly on the area where the Sterling Highway crosses the North Fork Anchor River, where there's a bunch of old culverts. So in the 1960s, they put these culverts in thinking it'll work really well. They buried them under 50 feet of dirt, and it was like super simple, worked really well. Issues are that it requires regular maintenance to clean up all the debris, because otherwise this gets backed up, which you can see over here. And if it doesn't always do that, which they don't always do, instances like in 2002, where we had a really extreme case where we had major rainfall and it all got clogged up, and it caused the road to act more like a dam, which is not what it was designed for, and it nearly washed out the road. So, which is what we don't want. So, because this road has the main access between Anchorage and Homer, and it's also the main access to the local community. And so if this road ever to wash out or close, it'll have a huge impact of the local area, and we don't want that.
So right now, given the current speed limit of the section right now on the Sterling Highway, it's going from 55 miles per hour transitioning to the crossing of 45. With our study, the 85% of the speed going between range of 52 to 57 miles per hour, we are designing our speed to 55 miles per hour. Before that, we'll talk about our decision matrix. This is what we need to successfully grade our decision. So first, we talk about safety. What we need to make sure is we want to fix those problems, make sure we make the design of the road, and make sure we want to minimize the traffic congestion at the same time when work exposure when we conducting construction. Also, we want to make sure it's friendly for both pedestrian and all the users. For environmental, since we want to minimize our land pollution, also improve the habitat of the aquatic system to make sure that want to increase the hydraulic performance of the river, and all of this will eventually reduce the permitting challenge and execution. For cost-wise, we want to make sure that the acquisition for right-of-way and utility relocation is less, and that's one of the things we have to consider. We want to reduce the impact with the nearby infrastructure, just like intersection or school, and also for constructability. We want to maintain the traffic. We want to make sure all those traffic keep continue flowing and reduce the construction complexity. And also, in maintenance-wise, we want to make sure what we build, we can maintain it and it can last for long, and it's not going to give us a problem in the long run. With those categories, we will use those to grade our alternative analysis from no-build upstream alignment, the downstream alignment, and the existing alignment. We begin with our no-build. This right here, going from 55 miles per hour. Additional problem that we having on this road, other than the culvert, is the curvature currently right on this location. Right now, it's at 6.7%, which is a 45 miles per hour on the rolling terrain. Is not in the standard because we're supposed to be 6%. But since we're designing on this 55 miles per hour, we will improve that to 5%. On the existing alignment right now, we're just improving the roadways, widening the road, going from existing of 4 feet to 8-foot shoulders. At the same time, to keep the traffic flowing, we are installing a temporary bridge right here, costs about roughly $1.5 million. And also, at the same time, this will cost us additional traffic control measure. Eventually will make the project execution, additional complexity with construction, roughly costing about $24 million project. To our upstream alignment, we are installing the bridges up north of the river, right here. On this right-of-way with our clear zone, we are acquiring some of the right-of-way, but nothing too big that we can't renegotiate with the current residential location. This is not impacting the current roadway, and we can keep the road open because we're building the bridge on the upstream. Altogether, this project will cost around $19 million. And at the downstream alignment, this, just putting the bridge down on the downstream side, will keep the road open at the same time, curvature, and all the designs still meet all the standard that we're looking for. With this, it has a major acquisition of the right-of-way and also major infrastructure reconstruction that we need to consider, which is the intersection. Additionally, Chapman School is nearby. Our clear zone is pushing to their parking lot. We don't want to compromise the integrity of their foundation. So at the same time, we are designing a retaining wall in that section so that way it can help out. This is the difference vertical alignment of all the segment. As we can see in this side right here, we are, this is what we're doing, our cut in fields. Downstream alignment, we're going to require more some cutting. This lane right here is where our planned abutment and retaining wall that we want to add so we can build our bridge. The design of this bridge is probably, this right here is the upstream alignment. Right now, it's about 200 foot and about 35 foot high. Same thing for the downstream, about 200-foot bridge span and about 40 foot high. And then the existing alignment, since this existing alignment right now, this current dash line 16 ground is the current road, and there is a culvert underneath here. So to bring that back to bring that to the standard of 5%, that has to go up a little bit higher, giving us a higher bridge and a longer bridge of 250 foot and about 60-foot high bridge. This is our the improvement of typical roadway of the rest of the corridor. So we are improving the 8-foot pavement of the shoulder from 4 feet. And now I'll hand it over to Orion so we can discuss about bridge.
Well, this river crossing area, it traverses a pretty wide and pretty steep span across the valley. If you could see from the vertical alignment, we're looking at around 60 feet high and 200 feet across. The first bridge we looked at was a steel girder bridge. We were able to design this with 5 steel girders. These are pretty heavy. You'll notice there's no piers in this bridge, even though it is 200 feet wide. We have about 1,000 pounds per linear foot steel girders, so they're pretty beefy to minimize deflections. This bridge ended up being the lightest bridge we looked at, but also by far the most expensive. And there's also maintenance costs associated with a steel bridge. But the picture you see on the left is another bridge on the Anchor River that's steel, so it can certainly be done. You'll see we've got 40 feet of drivable surface, just like the rest of the corridor. In the future, there could be 3 lanes on these bridges. And you'll also see we've got riprap lining the bank, and there's a retaining wall, a short one with a flat surface, and that allows wildlife and people to cross under the bridge. The next bridge we looked at was a 2-span concrete deck bulb T-girder bridge. These are really common throughout South Central Alaska. These are 100-foot spans, and you'll see that pier right in the middle of the river. We have six girders for this one, and same width and overall span. This amounted to about $10 million for the bridge alone, compared to closer to 16 million for the steel bridge. Certainly a winner in my book. And these girders are 5.5 feet deep, so it's a pretty big profile, pretty big project. We improved this in one way by going to a 3-span bridge, and this allowed us to go for less deep of girders. These are 3.5 feet deep, and we have the same number, so it's a lot less concrete, cheaper girders, and we did that by shortening the spans to be a 3-span bridge. These piles, you don't see in this picture, but they're going to need to go down a good 100 feet because the soils around here are really silty, poor load bearing capacity. So we're expecting pile groups of 4 to 5 piles, good 100, 120 feet down. But this ended up being a lot cheaper than going for the steel or longer span, heavier girder bridges. And there's a super elevation coming in and out of this bridge. So you'll see we've got the cross slope continuing. So there's a slight curve on this bridge in both the horizontal and vertical alignments.
Okay, so looking at the different alignments, looking and comparing them, you can see there's a good impact or improvement when it comes to environmental impact and maintenance for different options. The downstream and the existing alignments will have will require additional costs, mainly due to additional acquisitions for right-of-way. Or again, the existing alignment also had that temporary bridge, which also has a big additional cost and also has an impact on the construction. So weighing those different factors, scoring wise, our preferred alternative came up with the upstream alignment. So with the upstream alignment having smaller impact with right-of-way acquisition, mostly being some residential area up top, it's easier to procure and easier to get approved. So it's more likely to approve than the other ones. With also the bridge being not on the same alignment, being pushed upstream slightly a bit, you can keep the main road open throughout the project, which is very important to keep that traffic flowing and then we're not impacting that traffic. And also pairing it with our 2-span deck bolt T goes well with the cost, and also having the pillars just outside the water. It doesn't in fact impact the waterway, which also has quite a bit of fish in it, different species of fish. So we didn't want to impact that, and it worked well with the wildlife. Also, when we're doing this with the bridge, we're also trying to keep the bridge short, because as you'll see, the bridge actually, even though it was being all the way down to 200 foot, it still is the most expensive part of this project because bridges are expensive. These costs were based off doing cost estimation based on Alaska DOT's pre-construction manual and bridge manuals. So these are based on the actual costs of estimating in Alaska. There is some right-of-way acquisition, some utilities that are underground that have to be relocated. And then there's the road and bridge coming out to estimating about 19 million for this project. And I'll turn it over to my teammates for some lessons learned.
For lessons learned, we found it was pretty important to be on the same page for scope with your client. And I think this is true if you're a civil engineering firm or a Capstone group. It's important to make sure the scope is feasible to complete and also satisfies your client. To start, this was going to be a full 12-mile corridor and 35% plans, and probably was a lot to bite off for us. So probably should have gone earlier to make sure we were on the same page. And we also encountered kind of a domino effect of design. We were pretty intent on shortening this bridge to 200 feet. And one way we did that was by lowering the grade, and it ended up having some pretty big cuts that impacted the right-of-way in unforeseen ways. So it's important to not have tunnel vision when you're doing design and stay flexible. And finally, with software, we definitely had challenges with Civil 3D. The school computers haven't run Civil 3D this semester, and although we can get them on our personal computers, a lot of laptops are slow or can't get Civil 3D at all. So we ended up doing a lot of the CAD work from people's internship offices, which is obviously not ideal, but definitely a learning curve there with the CAD work.
That concludes our presentation. Are there any questions?
Is it that long of questions?
So given that this is a 30%, like less than 30% alternative right now, so we did all our design for alternative analysis so far. And the environmental concept permitting and all of those will be discussed at the end when we push further to our further design. So, well, the question is, just want to reiterate that if there's any coordination with the fishing game. Thank you. We'll put that into consideration. So this will be with our client, Aaron, and if he agree with our prepare analysis, and then we'll continue to push forward from there. If we are selected from that, then we can start going to true schematic design with more, including the road design. That's when we also including like the railing, all of those complete plan set that we're gonna put on, and then maybe we can push up to the procurement and we can start collecting what materials that we're gonna need. And then from execution from there.
Adding on to that, we'll also would be adding more, talking with the community, learning about all those permits, talking with wildlife, and making sure everyone has their different points met, and making sure all those little small things are hashed out, and so that all works out with their alignment as well.
Thank you.